You have the three, you've calculated the unknown of your, the concentration of your unknown of the original sample. You got the average and the standard deviation. And when you prepare your analysis report, which will look something like this, it's going to ask you for your unknown sample right here. Unknown 1, what is the concentration of the sample that we provided you? 12.7 part per million was the first one. Your second one, 12.5. Your third one, 12.5. You take the average, 12.6. The standard deviation of the mean, that's done here under precision, how reproducible your measurements were. So I have the formula and the answer. Make sure that you include the calculation, the whole calculation. So have all the numbers included here to show how you get to 0.1. Other than that, the only other calculations you're going to have to perform is the error propagation for each of these three unknowns. What is the error for of this concentration for unknown 1, unknown 2, and unknown 3? So I'll show you how to do that. Now what you see on this Excel sheet here is basically the same information on the other Excel sheet. So it's the same X values I have highlighted here, the same Y values. Again, the line-est output, that's all the same. Calibration curve is the same. I do have some new calculations and terms that I included here, and I'm going to need that when I perform the calculation for the uncertainty in my X value. So this is the formula I'm going to use. I'll just zoom in on this. So this is the formula you're going to be using. And you need to have all these terms to be able to do this calculation. And some of them we already had to begin with. So we're looking for the uncertainty of X, which is just expressed as a standard deviation. We have the error on Y. That was given to you in the line-est output. You got the absolute value of your slope, again from the line-est output. Your K value, that's a new term. It's how many times you measured your sample. So let's say for this experiment, I measured each of my unknowns once. K is equal to 1. If you measured each one 3 times, you would have K equal to 3. Your N value, that's referring to how many points on your calibration curve. So I have prepared 5 standards, 5 points, N is equal to 5. This term here, just zoom in again, your Y value, that's referring to your unknown absorbance value in this case. So right here. Y bar, that's the average of your Y values from your standard calibration curve. So I have that there. I took the average of it here to make things simpler. And you'll just simply subtract the 2, take the square. Underneath here, again, you got the slope. Again, you get that from the line-est output. And then summation of xi minus x bar squared. I performed that whole calculation in a cell here just to make things simpler. It turns out to be 2.5. It's xi is again going to be your values for your standard, and then x bar is just simply the average. So I performed all of these little calculations ahead of time, so when I do this whole equation, it doesn't make things too complicated. So what I have here, if you recall, this was the concentration of my first unknown before taking into account the dilution factor. So it was 1.27 if you recall. This calculation is going to determine what the uncertainty in that value was. And I punched it into this cell. So it's hard to see here, but this formula bar is essentially doing this calculation. And you can see, it might not be able to see, but all the values that are all the cells that are highlighted are simply these terms. So your SY is being highlighted here. You got your slope, your K value over here, your N value. All the terms and all the little calculations that were done in this formula are also being shown in here. And it just turns out that the uncertainty in that first unknown turned out to be 0.01, 0.06, or 0.07 actually. So once you use this formula, once you calculate the uncertainty in your x value, you need to backtrack, take into account your dilution factor. This uncertainty calculation refers to your diluted or your working unknown. And if we want to know what the concentration of your original sample is, we also want to know what the uncertainty associated with that original sample is. So we have to take into account the dilution factor. So what I have back in this slide here again, I did my tenfold dilution. I showed you the calculation, but what I'm also including in here are the uncertainties, because you're going to need these to perform that calculation, that uncertainty calculation. I'm looking for the error on my C1 of my original unknown. I know what the uncertainties of the other three terms on my C1, V1, C2, V2 calculation is. If I'm using a 10 mil transfer pipette, the uncertainty is going to be 0.05 mils. If I use a 100 mil volumetric flask to make my diluted unknown in, the uncertainty on that flask is going to be 0.08. The 0.07 on my C2, well, that I just calculated using the uncertainty formula on Excel. So I have the three values. I just need that last term. And since this equation involves multiplication and division, whenever you're performing propagation of error using multiplication and division, you just simply take the sums of the squares of their relative uncertainties. So if I'm looking for the uncertainty, the relative uncertainty for your C1, your original concentration, I need to know the relative uncertainty of C2, which I have here, just 0.07 divided by 1.27. The uncertainty of the relative uncertainty of V1 is going to be 0.05 divided by 10 mils. And then for V2, 0.08 divided by 100. So sum up the squares of those relative standard deviations, take the square root, you end up with a value of 5.5%. And 5.5% of C1, which I calculated to be 12.7, is going to be 0.7. So my original concentration is 12.7 with an uncertainty of 0.7. And that's what you would place here for your first unknown. And you just basically repeat that for unknown number 2, unknown number 3. Now I did this using, I did this one by hand, but you can easily perform this on Excel as well, just to speed things up. So after that, you pretty much have done all of the calculations for your analysis report. You now have the concentration of each individual unknown. You have the average. You took the standard deviation of that average, and you have the propagated uncertainty for each of those unknowns, all three of them. After that, then you can just simply place in a conclusion. In this case, I placed the concentration of aniline in the original sample was 12.6 plus or minus 0.1. So what this value is representing is the average of your three unknowns plus or minus the standard deviation, so what I had calculated here. And then just make sure you include the units. Have a short discussion. Usually it's a brief discussion of your results. Was it successful? Did it tie in with the theory? If not, explain any sources of error and any methods of improvement. Some of the experiments in the lab manual actually have questions for you to answer. So if there are questions, then this would be the area that you would answer them. If they don't, some of them don't, then just discuss your results tied in with the theory. So that's going to be some of the marks that are allocated, forgot to mention. 1 mark for all those calculations, placing in your concentrations, your errors. 1 mark for your standard deviation, showing the whole calculation. Your conclusion, short statement, 1 mark. 2 marks will be for your discussion. 1 mark for using the correct significant figures, so we'll be looking for that. And your accuracy is going to be 4 marks. So another thing to make sure is that you include the sample number on your analysis report. Every experiment uses a different unknown sample, so no one has the same one. So you need to include right up here where that sample number is of your sample. So when you submit your analysis report and your TA is marking it, they know which unknown to check your accuracy for. And your accuracy is only going to be as good as how well you perform the experiment. So if you know exactly, if you're doing things properly, if you're using the analytical instrumentation and all the measuring tools properly, proper technique, then you're going to get good accuracy. Otherwise, you're gonna lose marks for accuracy. So that's a total of 10 marks, where 40% of your mark is going to be on accuracy. Make sure you use correct significant figures. If you're using performing a calculation that has 3 measured quantities, and let's say 2 of those measured quantities have 4 significant figures, and the third one only has 2, then your final answer should be 2 significant figures. It's you only use is when you submit your final results, your significant figures should be limited to your measurement with the least number of significant figures. If you happen to not get a good mark on one of your analysis reports, you could resubmit it, do the corrections that are needed, but you will get a 10% penalty for that. However, getting 9 out of 10 is on resubmission is far better than keeping a 3 out of 10 on your first attempt. So it's good to do a resubmission if you need to. And what I showed for this particular example on how to prepare an analysis report may not apply to all experiments. Some of these experiments are going to be fairly qualitative, so you may not have to do any calculations whatsoever. So you may not need to know the concentration of your unknown, and there's no error calculation that may be associated with it. So you may have, a lot of those marks may be diverted to other areas. But because each lab is different, make sure you just talk to your TA about how to fill out that analysis report for submission. The standard addition method is going to be used on a couple experiments, and you use standard addition method for determining the concentration of your unknown in the case with your matrix components are too complicated, or if they are going to interfere with your analysis, then you would perform a standard addition method of determining the concentration of your analyte. There's actually 2 ways to perform a standard addition method. One is with varying volume, and another one is with constant volume. So this Excel file here, this sheet is showing you how to perform one with varying volume. And this one here is referring to how you do it with constant volume. Now I believe that experiments 2 and 3 involve using the standard addition method. Experiment 2 will use a constant volume, and experiment 3 will use a varying volume. So it would be important to know how to perform the standard addition method for determining the concentration of your unknown. And those Excel files will also be available for viewing. And again, this information will probably be available through your lecture notes